I'm going to discuss how we're gonna do the lecture this week. My older brother has passed away in Los Angeles this weekend. So he really fight through last 4 months to survive, but he couldn't make it. So I will attend the funeral and also arrangement of the funeral. My younger brother is there, so he and my nephew is also there. Whole Shinsu family is in LA area, so I'm gonna fly there today, and we'll come back on take off there Saturday. So I'll get back to Daejeon Sunday this week. So I want to give you a lecture today. That's why I really delayed to leave. And funeral service is going to be on Wednesday, so timing is okay. So, and right after lecture, I'll take off. And Wednesday, what I want to do, usually that's the way I did in the past. Again, underwater explosions, gas explosion, you've got to have a feel, which means understand the physical phenomena, because this disastrous act is not imaginable. So in that sense, I have a few explosion movie, videotapes, CDs and all that. So this Wednesday, I'm going to show you the Navy, US Navy, the movie is called The Close is Near Enough, which I want you to really watch carefully, because lots of phenomena in that movie, you will see that. It's unclassified. It's old movie, but explosion doesn't change whether it's old or new. Explosion is explosion. So underwater explosion is underwater explosion, and they have a lab test and bubble oscillation. All the features are there, so that will definitely help. Some of my students, Higyu, really involved and saw that the movie in the past, but Higyu is going to really take it and show you. So it will take, Close is Near Enough will take about 20 minutes. And the shipshock trier, USS DDG-81 shipshock trier, unclassified version, will take about 40 minutes. So both of movie will take about an hour. So about an hour. So you will see all features of underwater explosions. So that's how we're gonna spend next Wednesday. Even if I'm not here, I really wish you enjoy the movie and give some deep thought and try to get the feel of it. This is all gas explosion, underwater explosion, air explosion. This is all disastrous, the act. So it's unpredictable usually, but then if you can get more feel, it would be better to develop into the prediction method, things like that. And as you learn, you will see really connection between the gas explosion and underwater explosion. And the gas explosion, underwater explosion, both are equally difficult to predict. Maybe in some sense, some people could say gas explosion is more difficult. Some people who are really familiar with underwater explosion, they would say underwater, on decks is more difficult. Either way, as you are learning, I want to learn hard, then you will get the benefit out of it. There are very few experts in underwater explosion and the gas explosion here in Korea. So in one sense, to be recognized in the field, this is a very, very good area. Vibrations, noise control. Everybody feels they are the expert. Thousands of people. And you have to struggle to be recognized, but all this explosion, shocks, impact, penetration, very few people has some very good understanding. That's about all. Okay, I started last Friday, chapter 2. This is really beginning of underwater explosion. And this particular chapter is in a book called Underwater Explosion, written by Robert Cole, Professor Cole, who happened to be a professor in Princeton University. He wrote this book in 1946, all the days. Of course, he passed away a long time ago. He happened to be the professor of chemistry. And that's, he wrote this underwater explosion book. So since then, all the reports are available in the US or Australia, England, France, Netherlands, Germany, but usually not quite available. But internet search, if you go in there, you will see papers, things like that, but not many reports. As I start this chapter 2, first, physical understanding. For physical understanding, I'm always talking this. I wrote this long time ago, the sequence of underwater explosion event, the order of occurrence and physical laws and properties, and saying that what's the explosion? That's what I start explaining. What is explosion? I'm talking about explosion of explosives such as TNT, the HBX1, RDX, C4, all sort of the chemical explosive. And chemical explosion is chemical reaction in a substance. Substance means it's really basic component which really form up the explosive. Substance which convert the original material into a gas at very, very high temperature and pressure. This happened not only for on decks, it happened to gas explosion too. However, chemical explosion is more disastrous than the gas explosion as you consider in the vicinity of explosion. And whoever was here on Friday, we have just a few people. All the Professor Chang's lab you went to the workshop, meetings, things like that. It's self-oxidized. You don't have to, in any explosion process, you don't have to provide oxidizer. You just pick up from the air, and in the given environment, you don't have to do anything. It will just automatically process by itself, and it generates always gaseous product. Usually solid, explosive is a solid, then turn into the process into explosion, then generate high temperature and the pressure, then it generates the gaseous product. The difference between the air explosion and underwater explosion is density of the environment are totally different. So the density of the air is very lighter than the water. So when a gaseous product generate as a result of explosion in the water, then the water is the surrounding media, which is really holding the gaseous product. Then there is another process for the propagation of the energy still remained in the water. I'll talk quite more in a minute. And temperature we are dealing is 3,000. It's not just to say 3,000, about the 3,000 degree Celsius scale. But in gas explosion, anybody remember gas explosion? What would be a temperature range? Very high too. When fire is generated. And high pressure is something like a 50,000 bar. But gas explosion, we are talking about how many bars? Order of maybe less than 10 bars, 5 bars. Some are less than 1 bars. So nature is different, but how much the danger you have to consider, both are equally dangerous. And always changing from the explosion process is to make the unstable, the solid or compound into the stable, the gas, okay? And self-sustaining after initiation, extremely the rapid propagation reactions. For high explosive right now, simply speaking, when it explodes, of course, it will detonate, then a shock wave front formed up, then will move in the radial direction extremely fast. We are talking about 28,000 feet per second. Divide by 3.3, then you will get the meter per second, about 8,000, 9,000 meter per second, extremely fast. However, it doesn't move that fast all the way through. The speed will drop exponentially and converge to what speed in the water? Converge into what speed? Younggun, what speed? It's going to just 8,000 meters per second. Is it going to propagate that speed all the time, or what happened? Converge down to acoustic speed in the water, right? That's the lowest it can go, then acoustic speed in the water. So at the beginning, detonation speed, right? Then exponentially decay and converge into the acoustic speed in the water, okay? Which is, what's the magnitude of acoustic speed in the water? Sonic speed in the water, what is it? Who cares? 1,000 is about 1,500 meter per second. That's what usually converging that speed and propagate out. That's what the shock speed we are talking about it. Okay. And there are two different types of explosive. So I call here is types of the disturbing process and energetic material classification. Before getting to that, we already know this well, but I'm going to distinguish between gas explosion and the high explosions. And the detonation, you know that. Detonation, as you consider the bomb stuff, high explosive is such as a TNT. Everybody feels already TNT. Oh, that's a very high explosive. So which detonate with a large and rapid evolution of the energy. Bombs, depth charge, torpedo warhead, or torpedo itself, and burning. Combustion is a burning. And the propellant such as gunpowder, which burns with a gradual build-up to final stage, burning, combustion. Deflagration is rapid burning, faster the combustion. So we have a lot more information already. So combustion, deflagration, faster, rapid burning, and detonation. So what's the difference among these three? Speed is a function of the pressure, which is less than the sound speed. That's what the combustion is, subsonic speed. We know that. And the detonation is speed is higher than the sound speed, which is supersonic. Okay? And combustion, burning is a very slow process, but detonation is extremely fast process. So we are talking about detonation 8,000 meter per second, 8 or 9,000. And combustion, I generally said small pressurized. Detonation is a large pressurized. And here, of course, in this case, is unconfined situations, not internal explosion, rather say external explosion. And confinement changes the pressure. That means when explosion occurs inside the tank, that generate really power. And for combustion, more energy release. Detonation, more power it generates. And what's the difference between the energy and power? What's the difference? Power is time derivative with respect to time derivative of energy, right? That's what the power. Time rate change of energy. So even if you're dealing with a small energy, when you are talking about the time derivative, then that's a very detrimental, very dangerous, okay? And all these phrases, I put it in as a reminder when I give a lecture. Then, but you can really read this. There is no difficulties to understand. It's just my own writing. So, for example, explosive do not usually have high energy content of ordinary fuel. However, the rate of energy release, time rate change of energy during the explosive chemical reaction process result in greater destructive power. So I want you to read, in explosion, the process ends very fast. It's different from gas explosion. For this high, when you deal with a high explosive, everything is done in terms of a millisecond. 1/1000th of second, process is done. So after a few milliseconds, as you saw many TV news in Middle East, it's so quick. Life and death is right there after a few milliseconds. So, but the gas explosion is a difference because the fire is keep continuing. So that's really more dangerous in a sense to kill the structures, human life, and so on. Don't overlook. Please read this. All little phrases. You are dealing with the water. Explosion occurs in the water, and dynamic property of the water. So we're going to deal with the water. In explosion in the water, we are going to deal the homogeneous fluid with no shear stress capability. Homogeneous fluid media is what we are dealing. But if you deal with the ocean acoustics, this is no longer true. This is really dealing explosion in the water. So if you look at the vast ocean, the ocean can be divided with a few different layers. A thermal layer, and temperature is different. And the temperature is different, and also pressure, water pressure, ocean water pressure is different. And then so-called caustic effect occurs here. For example, this is sound source. Something like explosion occurs right there. Or you put some active sonar right in there, then it generates the sound. It doesn't propagate. Of course, there is some portion will go through, which is not high, because of the property of the ocean water. Is so-called caustic effect is coming. Sound propagate through like that. Ga을기, when you work at here, 해양 연구소, you know all this one, this kind. Caustic effect, no? Okay, because he's dealing with a ship motion, which is near the surface. When you're dealing with a submarine, you have to deal with so-called caustic effect. But anyway, when you deal with underwater explosion, just assume homogeneous water is good enough. You don't have to dealing with inhomogeneous water property. Water propagation speed is 4,900 feet per second at 18 degrees in Celsius scale. For the design purposes, you don't have to worry about it. For design purposes, you can assume the 5,000 feet per second. That's good enough. That's perfect for design purposes. But if you gonna work on the analysis problem to really find the exact, in a sense, then you have to measure the temperatures and the speed. But again, I will show you the empirical equation to get the speed, okay? the acoustic speed, which is function of temperature and salinity, and pressure is the secondary term. And velocity, I said, is dependent on pressure magnitude. However, for small scale amplitude wave, velocity is constant. You can assume the velocity is constant once you find the temperature, ocean temperatures. Then salinity is somewhat important because the salt content is what the salinity is. Of course, between the river and the ocean, salinity is different. In river, salinity is 0. And the Pacific Ocean and Indian Ocean, salinity is different. Temperature is different, big difference. So that you might have to consider to dealing with wave motion in different area. Otherwise, velocity, acoustic velocity, 5,000 feet per second or 1,500 meters per second, that's good enough for design purposes. And we are dealing with two different wave propagation. One is a plane wave propagation. Another one is spherical wave propagation. When you are dealing with target motion, where the explosion occurs, the close to the target, then you are dealing with the spherical wave. Spherical wave has a curvature, okay? And when you consider the curvature of a shock wave, fluid particle velocity is also the function of the curvature of shock wave front, because it will propagate. And a near side position from the explosive is really radius of a spherical wave is very small, which means it has high curvature. And the velocity is, the fluid particle velocity is affected severely by the curvature of the shock wave. But as it moves a really long distance, then virtually, God bless you, virtually there is no curvature, which means the acoustic velocity, the fluid particle velocity is very less affected by the curvature. It's almost flat, okay? So shown here, so plane wave. Plane wave is one-dimensional wave. It's like a step function, okay? It just moves. There's no change in pressure magnitude. It's just moving in, let's say, x direction. That's about all. But for the spherical wave, amplitude is a decay, because as it propagates, shock wave front. Think about the surface of the sphere. As it's getting larger, then the surface area is getting larger, which means total energy or pressure in the sphere is constant. So as the surface is larger, the force per unit area, which means is a pressure, is getting smaller, smaller. How much is smaller? Proportional to inverse of the radius of propagating the sphere. So equations is all coming in a minute. So that's what that is. Plane wave, we are dealing with a plane. Shock wave, we are dealing with spherical shock wave. pressure wave and the reacting explosive begins outward motion of the water. So just as an example, showing the pressure magnitude. And the conversion between the PSI and the megapascals I gave you, but you have a conversion table so you can readily see. 1 kilopascal is something like a 6.8 megapascal, something like that, okay? So again, US is using US gravitational units, not really metric, but nowadays US is using both metric and US gravitational. But as school, you should learn both the units, metrics, and also US gravitational. And conversion table is always right there. Then it really doesn't make any difference. And over here, pressure wave, explosion, and exponential decay. This is really, as you just pick any point here, then shock wave will propagate in radial direction. I'm standing right at one point, then feel the wave is just moving away, going away, so that's exponential decay. So I just draw that. And that time is a few milliseconds, done, okay? This is important. In Cheonan naval ship, when such an accident, it's not the accident, incident occurs, people are talking about really, they are not talking much about the shock wave, but they are talking about the gas bubble. They are not saying gas bubble. What was it? What do you call the Koreans really invented the word bubble. Anybody can? I forgot. What do you call that? Gas? It's a well-known name. In those Cheonan incident time, Korean whole people really made up that name. Bubble? What do you call it? 뭐라고 그러지? Well, let me think. I even wrote monthly, the October newsletter about that. I forgot. Anyway, this is a very important process. When an explosion occurs, okay, this is talking the gas bubble oscillation. If explosion occurs in the air, the oscillation never happen. But when explosive detonate in the water, then gas bubble oscillation occurs. That's a totally different ball game. And that gas bubble oscillation is detrimental to the ship, naval ship, or any ship is detrimental. So what does it mean? When the explosion occurs, the first thing it does is it generates the shock wave, and shock wave will propagate extremely fast. And like a detonation speed is like, I talked already a few times, 8,000, 9,000 meters per second. and shock wave is moving fast and going away and done, okay? But still the gaseous product remains in the water, then it has energy in there. Energy is concerned, the shock wave does not carry away 100%. About 52% is not absolute value. About 52% carried by the shock wave. When it hit the vessel, then it's going to really get hurt, okay? But still about 48% remain with the gaseous product, which is called the bubble. The gaseous product, the generated, remain in the water is called the gas bubble, or simply the bubble. Okay, when you talk here, we're gonna call that as a bubble. That gas bubble, energy is in the gas bubble, then of course the gas bubble size will grow because its energy is there, and it will grow. It will grow, as I mentioned before. How far is going to grow? Songtae, how far is going to grow? Who cares? We care. How far is going to grow? As the gas bubble grow, what happened? The shock wave, gas bubble pressure is getting decreased. Why? Because gas bubble size is getting larger, right? So surface area is getting larger. Then naturally the pressure is getting decreased. Then there is external, of course, pressure in the ocean depend on the depth, right? What's the pressure? Atmospheric pressure, 1 bar or 14.7 psi plus the depth. Because as depth depend on where the explosion occurs, that depth will generate hydrostatic pressure. So the gas pressure at some point as gas bubble grow, when it's equalized with atmospheric pressure plus hydrostatic pressure, when it equalizes it, it can't move any farther. But because of the inertia, the effect is going to move a little bit. As I mentioned Friday, when you push the brake in the highway, high-speed highway here, if you push the brake, you can't stop the car right there because it will skid because of the inertia effect. So gas bubble cannot stop when it equalizes with the external pressure, which is atmospheric pressure plus hydrostatic pressure. It will move, then stops, then start to shrinking because during that time, energies keep radiating into the water, keep losing the energy. Then it will shrink it. It will shrink and shrink down the minimum. As you get down to the minimum, as you look at the sphere, and top of the sphere, gas bubble, bottom of the sphere, the pressure is different. Because which is higher? Bottom pressure is higher than the upper pressure in the gas sphere. Then pressure in the bottom is pushing upward direction, right? Say yes. Yes. Upward direction. When the pressure is high at the bottom of the gas sphere, is pushing up, then the bubble lose the balance. Bubble lose the balance, then the gas bubble collapses. Whenever things collapses, it generates the sound, explosion sounds. It loses. So that's a secondary pulse or secondary shock. Joel, look at my face, look at me. You have to look at me. Otherwise, a lot of experts is doing the work. They don't know this process. So when I go around the world, we trained so many experts, over thousands of people who is involved in the explosion. That's what happened. When the gas bubble loses the balance, then a bubble collapses. But as bubble collapses, still that is in the water environment, which is different from air. For air situation, there is no such a thing as a gas bubble. Gas bubble doesn't form. It just explodes and propagates away because air density is so small. Then that's what happened. So now it collapses, but still energized gaseous product is still inside the water. And some of the, of course, energy is radiated by the expansion and the contract. So keep losing the energy in the bubble. So does it stay down at the point where it explodes? Does it just doing the gas bubble? It's called the gas bubble oscillation. Is it the gas bubble is going to oscillate at that point? No. It's a natural phenomena, is what we are living, what we are subjected to. Because when you dive in the water, can you stay down forever? You have to always what? You have to come back up. Why? You have to come back to the surface to breathe, right? Say yes. Same thing. Similar phenomena. When gas explosion occurs in the certain depth, let's say 100 feet below, then as it oscillates, as the gas bubble oscillates, it doesn't stay down there. It has to migrate toward the free surface. Migrate means moving up toward the free surface as it oscillates. Why does it do that? By the what force? What force? Buoyant force is there, right? Buoyant force. What's a buoyant force? The buoyant force is the force, the force displayed by the volume of the gas bubble, right, times G. That's what the buoyant force. It keeps pushing up. It's going up. As it goes up, still bubble oscillation occurs. Make sense? Gas bubble collapses. The gas, the bubble energy is still there. It expands again, then hit with the external pressure wave, then moving back, contract down to minimum, collapses. So as it goes up, expanded, then going down, collapses. As it collapses, the gas bubble comes upward direction faster than the gas bubble is large. That's one of the questions, students' question when we give a lecture in Connecticut, where the I even forgot the name of the town, where the dynamic the submarine is built. That's what Groton, Connecticut. So when we give a lecture out there, one student raised a hand saying, "Why the gas bubble is coming? Gas bubble is small. The gas bubble moves faster. Why?" That's what the experimental result shows. I couldn't answer, and I have a colleague always working together to give a short course that we couldn't figure out, came back. Then we figure out, next day we explain, and I'll show you what that is. Anyway, gas bubble collapses and going up, then expanded, then shrink it, going up. Finally, when the gas bubble reach to the free surface, then venting occurs. Venting means, as you look at the movies on Wednesday, watch carefully. When it goes right into the free surface, then it venting out in the air. And when the venting occurs, all the stuff is no longer white stuff, it's all black stuff. Okay, that's what the TNT gas, the residual is. But another important fact is this. This kind of the lecture, you are not going to hear from any other place. It's all phenomena. A lot of people doesn't know this phenomena. When the gas bubble, whether it's a large or small, it reach to the free surface. Right above the free surface, what's there? This is atmospheric pressure, right? 1 bar is all there, occupied in all airspace above the water, okay? That's their territory. But now bubble is trying to come up above the free surface. They don't like it. Say, hey, don't come. This is my territory. You should stay down. I have a weapon called 1 bar, 14.7 psi. When the gas bubble tried to come up to venting by the buoyant forces, then keep saying, don't come down, keep tapping. So when the gas bubble tried to vent, cannot vent out to the air. It comes down below the water. Few times, because the atmospheric pressure is pushing it. Then eventually, hey, I have to go. Then come right out, it's all the black stuff. However, when you watch the DDG-81 ship shock trier, they use a 10,000 pound charge, which is really 5,000 kilogram charge with classified distances. You will see that all this phenomena, even if gas bubble doesn't vent out, you will see all the white plume there. All the white plume comes first. This white plume is caused by the bubble collapse. Right? Bubble collapses below, right? When it equalizes with the external pressure, then it shrinks down to minimum. Then, because of the buoyant forces, bubble collapses. It generates a pulse, which means it's a secondary shock. The secondary shock pushes the water, the particle. Then that's all the white plume. When you see the white plume in the ship shock trier movie, then that's really due to the bubble collapse. Depend on the depth of the charge. You could see 2 gas bubble, or 3 gas bubble, or 1 bubble, or no bubble, just venting out. When the venting occurs, when you see the black stuff, that's a venting occurs. Then the process of explosion concluded, okay? So that's the process. It's understandable, right? 공식? And in gas explosion, you don't have such a gas bubble oscillation because it's usually air. Eventually air. Of course, the explosion occurs with a mixed medium situation, but fuel is there. but it's all surrounded by the air. Air density is very small, then there is no gas bubble oscillation. Okay? And you will see, I want you to read all this phrase, okay? And all this phrase, that deflagration, detonation, combustions, detonations. And lastly, I want to read this interesting phenomena. As I see in Korea, you don't have old car. It's almost all new car. At least 10 years old, longest. He always has a good car. But in US, there are lots of old car. And for the old car, there is a phenomena called engine knocks. Engine is knocking, bang, as you drive it, which means it's really a small explosion occurs when the engine runs by the pistons and all that. Piston process is really small explosion process, but for the new car, you don't see the knocking. But all the car, engine knocks. That's what really the daily experience for detonation. So as I shown here, example of combustion change to detonation is knocking in the auto engines. When the detonation retard into the combustion, explosion is very much less effective. An explosion which degrades combustion is always usually referred to as a low order explosion, or people call the misfire. You heard about misfire? Maybe not popular here, and which means you have a good life. When I was in graduate school, I bought did I buy the car? No, my friend, he bought the car. I said, how much you pay for it? He said, $50. What, $50? Then he said, I'll give you a ride. And okay, so I sit next to him, but I can't, the door closed. This is only $50 car, so I have to hold the doors, you know. But you never have such experience here in Korea. So that's what we have. When I was in graduate school, that's what happened. So we really have a lot of fun with the $50 car. There is no $50 car here. Right? No such a cheap car. $50. So that's what happened. Okay, I'm spending, as you realize, a little bit time this chapter. This chapter explains all the phenomena for index, and next section is dealing with the conservation law. I want you to read my note line by line. It's going to help you tremendously. This would be a last time to understand the conservation law in the practical sense. Then you can see my note to specialize into the deriving the wave equation and solve the wave equation to get the most important equation. P is equal to rho CV type of the equation, which is very important doing the shock wave analysis or underwater explosion analysis, okay? So this would be the last time because I'm not going to be around to teach next year. Next year I'll teach on spring and fall quarter. That would be the last. Okay, I'll see you Monday next week.